Okay, so today we're a little behind because we missed a day of class, and so we just postponed the homework assignment for one day. And today what we want to do is, the topic is symbols. Now these are assembly language symbols. Now let's remember, what is the fundamental question of computer science?
What can be automated?
Excellente. What can be automated? So you know how whenever you, so far whenever we have an assembly language program or machine language program, you put the data somewhere, and then when you branch around the data, you have to count how much space is taken up by the data to figure out where to branch to. You remember that? And also, whenever you want to load something from where that data is, you have to figure out what the address is. Well, look. What can be automated? Counting. The assembler can count how many bytes are generated by each line of code and can figure out where those items are going to be. You see what we're saying? So this is a great feature now of assembly language, and we know because we have programmed in machine language, we know what problem it solves. It solves the problem of having to count up and calculate those addresses for the instructions and for the data. So a symbol is defined. What you do is you put it in your source code, and it's an identifier. So it starts with a letter and has to either have letters or digits in it, and it ends in a colon. So that's how you define a symbol. It's an identifier followed by a colon at the start of a statement. And here's the key concept. The value of a symbol is the address of the object code generated by the statement. So just remember this. What is the value of a symbol? It is a what? The value of it's a what? It's an address. The value of a symbol is an address. Okay, and we will illustrate symbols with this figure 5.15, and we'll do a little demo of it here in a minute. And this is that problem that takes, here, let's remember what the output is on the next slide. So if the input is negative 479, what it does is it inputs it, and then it outputs negative 479 plus 1 equals negative 478. So remember that program? We did this without symbols before. So now here it is with symbols. So now check this out, you guys. Look. Normally, when we said branch to somewhere, what did we have to say? We had to say branch to what? 0x0005. But look, instead of having to branch to 0x0005, what do? In front of the first statement, that decimal input statement, we put a symbol. We call it main colon. And then when we branch, we don't have to branch to 0005. What do we branch to? Main. And what can the assembler do? The assembler can literally count up how many bytes are generated from the start and figure out where main is going to be in main memory. And so what is the value of main, do you think? What did we say the value of a symbol was?
003.
Yes, the value of main is 0005, because that's the address of where the statement that is labeled with main is. Is everybody clear on that? And look, when we reserve storage for a number, you see with that dot block 2, now what did that dot block 2 generate? That's a dot command. What did that generate? What did that dot block generate? Those 2 bytes of zeros, right? But look what we have in front of the dot block. We have what? Num colon. So that defines a symbol called num. And what's the value of num? 0003, because that's where in memory that quantity is. And furthermore, we have the stro output, right? String output. And instead of doing string output from 001B hex, hex 001B, where do we do stro from? Message. And what's message? A symbol. And the assembler calculates, and now tell me, what's the value of message? 001B. Now, is this cool? Now you can just put a symbol in front of each statement that you want to have to reference from somewhere else, and the assembler will calculate where in memory that quantity is. Yeah.
So the symbol itself doesn't take up any memory.
That's correct. The symbol, good point. So the point was the symbol itself does not take up memory, and that is correct. So what happens is the symbol, when the assembler sees an identifier followed by a colon at the front of a statement, either a dot command or a mnemonic, what it does is it has been calculating, it calculates how much code has been generated before that point, and it calculates where that's going to be when it gets loaded.
Okay.
And that's inside the assembler. So and that's done with a symbol table. Hold your thought one second. And then on this next slide, what happens is in your listing, after the listing, there's always a symbol table. This is called a symbol table. All right? And you see, what does the symbol table give here? A list of each what? Symbol and its value. And you notice that what's the value of main? 0005, because if we come back up here, main is going to be stored at 0005 when it gets loaded into memory. Now, is that cool? Okay, now, question?
So,
yeah, actually what happens internal, that's all internal to the assembler, is how they get defined. And what happens is, inside the assembler, what it does is it keeps track of how many bytes are generated each time it generates code, and then when it sees the symbol, it knows how many bytes have been generated up to that point, and then it stores that internally in a table, in a symbol table. So that's internal to the assembler during translation. And like the point that was made previously, the symbol itself doesn't take up code, it doesn't generate code. You see how that, is everybody good? Okay. Now, so let's demo, actually before we demo this, there's one more item that we need to look at. Notice that this in num, the second line of the assembly language code, the symbol num is .block2, and what does the comment say there? Storage for one integer, and then what do we have? Yeah, that pound 2D, so this hashtag or whatever. Okay, so this is called a format trace tag, and these are required from now on. Every program that you write is going to have symbols, and they have to be annotated with these trace tags, and we'll demo what this does in a second. But this hashtag 2D means, this is what it means. It means 2-byte decimal. 2-byte decimal. And what it is the debugger actually goes through, and in the comments it looks for this hashtag marker, and it will actually analyze the comments and pull out the information from the comment and use that information in order to do a symbolic debugging. Okay? So now, I'm going to demo that now. Yeah, question?
How come that's the only one that's labeled?
Yeah, because that's the data. That's the only one that's data. The other ones are program statements. Yeah. So this is like, so this num is like, now what is, I have looked at some of your exams. One of the questions was, what's the C memory model? So what's the C memory model? Globals, fixed location in memory, and then locals and parameters on the runtime stack, and dynamically allocated variables from the heap. So this is like a global variable. So where is it stored?
Fixed location.
At a fixed location in memory. Now watch this. So let's demo figure 515. Okay, so here's our demo, and let's go to the help system and look at 515. That should be that program we just looked at. And so here's the program. And if you see here, there's that hashtag 2D here. So we can copy this to source. So here's our program, and as if we were to type that in, that would be all good. And then let's build it. And when we build it, we get the assembly language here, and we get the listing here. All right? And here is our input is going to be negative 479. So, are you ready for this? Watch this. Let's start debugging. Boom! And what comes down here? What is this 0030 num? That is at a what? Fixed location in memory. And this particular program doesn't have a runtime, doesn't use the runtime stack, so that's not going to be in play, but is everybody clear on that? And look, that num, what happened was the debugger associated this #2d with this num. Okay, and so it labeled it, the symbolic debugger labels it num here. And this #2d says, whenever you put a value in here, display it as a 2-byte decimal number. That's what that means. Because we are interpreting num as an integer, right? So check this out, you guys. This is so cool. Single step, watch this. Okay, so we did branch to main, right? So now Deci is going to execute. Now what does Deci do?
Takes the input.
Decimal input into where? And look, into where? Num using what addressing mode? Direct addressing. So now we don't have to say decimal input into 0003, we can say decimal input into num. Because what is the value of num? The value of num is 003. See, look, the instruction itself is 310003. See, just like it's supposed to be, if you did it without the symbol. Yeah, question?
So basically these don't change what's actually happening in memory, but it changes how we write out what's happening.
Yeah, that is a very good observation. What it does is it's a more convenient way to write what you would have to write in hex. It doesn't change the way the program is written if you were to write it in hex, in machine language, you see, without the symbol. Does everybody see that? So decimal input, 310003. So when we single step this through, what's going to happen? What's going to go where? The what? The negative 475 is going to go to where? To 0003, which is here. So check this out, single step. Boom, there's a negative 479. Is that slick? Are we good? And now what is Deso going to do? Deso from where? Num. So this is I need my glasses. So that's 390003 because now the value of num is 0003. So when we do this decimal output, what's going to come out? Negative 479. And now what is this? String output. And string output what?
Message.
From message. But wait a minute, what's message? See here, it got translated as what? 49001B. So if we go down here to what the heck is that 1B? Well, see, it's this message. This plus 1 equals. So if we single step that, plus 1 equals. And now, what is this statement? Load what? Load word accumulator from where?
Num.
From num. So what's going to happen up here in the accumulator? Haha, what's going to happen in the accumulator?
It's going to be good.
It's going to get the negative 479. So boom, see, it's actually FE21, but that's negative 479 because you know how to do sign bits. Da-da-da. Are we good? So there's the negative 479. And then this next one's going to do what? Add accumulator. Now what's it adding? 1. But what's the addressing mode? Immediate. So does that mean we go to address 0001? Yes or no? No, that means we add the 1 because it's immediate addressing. Is everybody clear? Okay, so we single step that, and look, boom, now there's the negative 478. And now what do we do here? Store word into what? Num, direct addressing, and so what does that do? Boom, there's the negative 478. And see, it's in the debugger, the symbolic debugger. Is that slick? So now you don't, you could go through and, do it all up here. You could trace through here in the memory dump, but now we've got this, see? Now we can do it symbolically. We don't have to go in there and muck around with that, with that memory dump. We can do it symbolically because we have num right here. And then now what is this deso? There's the negative 478, and then we stop and we're done. So that's the demo. Okay, so that was the demo, figure 515, and all done with symbols. Now, aren't symbols great? I think they're just really nice. But we have to understand what they do, how the assembler does it. What the assembler does is it counts. The assembler knows how to count how much code gets generated. And so now, and I promise on the next exam, I will give you another problem like I did on this previous exam. It'll be given the symbol column and the mnemon column and the operand column, and then you'll have to fill out the addressing column and the object code column. So you have to know, you have to understand the mechanism of how symbols get calculated and the code that gets generated. Is everybody clear on that? So this is be a favorite exercise for the homeworks as well as the exams. Okay, but now here's the thing, you guys. Here in figure 516, now you have to understand that with symbols, we're getting kind of like a higher level of abstraction, but you still what's going on in the underlying code in the machine is still the von Neumann cycle. That doesn't change. Just because we have symbols to do the translation, the von Neumann cycle is still cranking through, and all these things can happen still with the von Neumann cycle. You can have a program that modifies itself. You can interpret instructions as data. You can interpret data as instructions. So look, what does this nonsense program does? If you just took a look at that top listing, it says this colon, deso, this comma d, and then stop and dot end. Now what the heck does that do? Apparently, what does it say on the output? What comes out? 14,500. How in the world? I don't see a 14,592 in that program anywhere. How the heck does that come out?
Does it get randomly whatever is that address?
It gets what's at that address, but not randomly, because we should be able to know what is at that address. Because what is the value of this? No, hold on. This colon is a what? It's a symbol. What's the value of a symbol? It's an address. And so do you see what's the address? So what is the value of this? It is 0000. So do you see that the code, what code got generated? 390000, right? That's the code that got generated. And what is that statement? What is 39? Okay, so what is 39? 39 is what? 0011 is the 3, and the 9 is what? 1001. Okay, so now, what is the 0011? Anybody? You want to look that up? This is the what? This is deso. Using what addressing? Direct addressing. All right, so this is direct addressing. Actually, this whole thing is the deso, right? Using direct addressing. But so it's decimal output from what location? 000. Well, what are the bits at 0000? What are they? Can we tell? It's 3900. Are you with me?
So it's outputting.
Yeah, so 3900. Let's write this in binary. What's the 3? Oh, we just did it. 0011, 1001, 0000, 0000. Right? And so it interprets this as a what? As a decimal number. What's in the sign bit? What does it interpret as? 0, so it's a positive number. So what is it? 1, 2, 4, 8, 16, 32, 64, 128. What is this? 256? 512, 1024, 2048. Oh, we need to do it 2 more times. 4096? 4096. 1 more time. 80. 8 what? 8192. Let's add them all up.
14,500.
Oh, what do you know? It's 14,592, I think. Is it? Has somebody done it?
No, but
Anyway, so look, so all that stuff that goes on in, the von Neumann cycle and, and interpreting bits one way versus another way, none of that changes with symbols. Is everybody clear? None of that changes with symbols. I could demo this, but trust me, this is what happens. All right. Now, the next thing the next thing that we're going to do is we are going to look at not only how, we've already looked at what an assembler does. Now, what does assembler translate from? From what level to what level? An assembler translates from what level to what level? From ASMB 5 to where? ISA 3. Is everybody clear? From 5 to 3 is an assembler. But what does a compiler translate from? Here, according to figure 5.18. HOL 6. Right? So it translates programs like C or Java or C++. That's what a compiler does. Right? Now, it's actually quite common both of these compilers are common. We have type 1 in figure A and 1 in figure B. Part A of the figure and part B of the figure. In part A of the figure, what happens is the compiler translates directly from HOL 6 to ISA 3. Are you with me? But it's quite common for compilers to translate from HOL 6 to ASMB 5. But if the compiler goes from HOL 6 to ASMB 5, then what do you have to do before you can actually run the program?
you have to go from ASMB.
You got to invoke the assembler and go from ASMB 5 down to the ISA 3. And that's actually common. It's common to do. Both of these are common. But so what we are going to do is from now on for the rest of the course, a large part of the course is going to be understanding how the compiler translates from level HOL 6, and what we're going to do is we're going to do it as in part B. Okay, we're going to do it as in part B. In other words, we're going to go from high order language to assembly level, and then we'll know how to go from assembly level to machine level. Okay. So what our job now is to see some simple C programs and understand how the compiler translates from level HOL 6 down to assembly level. All right, so here are some guidelines on how to translate the C printf statement. All right, so if you ever have to output a string, then you do that with stro. Okay, so like if your printf wants to output a string, then the way that gets translated is with the string output instruction. If you ever want to output an individual character, you do that with store byte accumulator. And now look, what do you suppose char out is? Char out look, you guys. Char out is a what? It's a symbol. It's a symbol built into the assembler. And now, do you remember where is the output device? What was it?
FC15.
FC15 or FC16?
Output is FC16.
Oh, yeah. So guess what the value of char out is?
FC16.
Yeah, that's the value. So now you don't have to remember that. You can just use the char out symbol. Yeah.
Is that something that it knows already because you can't like store it as that?
Yeah, actually, there's two parts to an output. I mean, if you have a character a char variable, then to output it you would load byte accumulator and then store byte char out.
Oh,
I don't know if that was your question
my
or
question
not.
more like, so on the other one we labeled main : And it,
Oh, I see. Oh, yeah. Oh,
160.
that was a good question. Yeah, so what's going to happen is that char out colon, that is that's a symbol from the operating system. Because, because it's wired into it's memory mapped I/O. So that symbol is actually defined. There is char out colon, but that is literally in the operating system. Yeah. So is everybody? Yeah, that was a good question because that's where it is. It's wired in. It's a part of the operating system. Is everybody clear? Okay. And then the way you translate an integer output is with deso. So here's an example. This just has a string. Okay. So here, just to illustrate the compilation process. So here our C program is int main, just printf, hello world, bash n. What is the bash n? The new line character, and then return 0, and boom, that's it. Okay, so we're not even going to bother to branch to main because there's no variables in this program. And so basically the way you translate that is with stro, and then message, comma, direct addressing, and then stop. And then, do you see MSG colon is a what? And what is the value of MSG colon? What is the value of MSG, the MSG symbol? What is its value? 0004. Because you see, when it says string output to message, what is the code that got generated? 49, then what? 49, then what? 0004, because the value of message is 4, is 0004. Now, is everybody clear on that? Does everybody see how this is all linked up together? Okay? And then the message is, so oh, by the way, always put your strings to output after stop. Don't put them up, don't branch around those and put them up at the top. That's our convention, is to always put the .ASCIIs at the bottom, after the stop and before the end. So look at that ASCII string. It's double quote, hello, comma, world, exclamation. And now what is that bash n? That's the new line. So that's because we have the bash n up in the original program. Are you with me? And why do we need the bash x00? The null character for the string output instruction. And do you see, what do you suppose 48656C is? 48 is probably what? H, and the 65 is the E, and etc. Is everybody clear? Okay, so that's how that gets translated. All right. And here in figure 5.20 is a graphical depiction of exactly what the compiler does. Okay, so remember we had two kinds of compilers. A compiler that would translate directly into machine language would take what? That C program, int main printf hello world return 0, and the processing would be the compiler. Are you with me? So the input to the compiler is a what? What is the input to a compiler? A what? An HL6 program. And what is the output of a compiler if it compiles directly into machine language? It's that what? Yeah, there's 490004, 00486566, blah, 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 blah. Does everybody see? Literally, that's what it... Look, these translators, all they're doing is they're just taking one string of characters and outputting another string of characters. That's all they're doing. That's all the translation does. In this case, the string of characters is a C program, and the string of characters that get out is the hexadecimal machine code. Yeah.
So what's the point of a compiler taking it to assembly language first if assembly language just has to be translated to machine language?
Yeah, that's a good question. The question is, why do it that way? A really important and common reason is because you might want to, a human might want to go in and inspect and actually modify the assembly language code to optimize it further. Okay. Yeah. So it's for human intervention, and for us, it's so that we can understand. We don't want to have to deal with machine code. Okay, but look at part B. Part B is the compiler that takes the same program, but this compiler translates into assembly language. So do you see then that the input is that same HOL6 program, but now the output is assembly language. And then it would take an assembler to go from the assembly language to the machine language. Is everybody clear on how that works? So every computation takes input, does processing, and produces output. And this is the computation that's done by a compiler. Does everybody see how that works? Okay. So like I said here in figure 5.21, instead of doing it as in part A, a compiler that goes directly to machine language, we're always going to go from HOL6 to PEP9 assembly language, and then to machine code. But now here is the point, you guys, and this is another reason symbols are so neat. Okay, so let me write this down. A symbol in assembly language corresponds to a variable name at HOL6. All right? So what we're going to do is the symbols in assembly language, they can only be at most 8 characters long. So we're going to deliberately name our variables, give our variables short names at level HOL6 and C. In a real compiler, you know, in a real assembler, you can have really long identifier names and stuff like that. But anyway, is everybody clear? Okay. So now let's do another translation. So to get set up for that, global variables, where are global variables stored at a what? Fixed location memory. And how do we allocate them? With what? Dot block. Okay. So if you have a character variable, that would be dot block what? Characters occupy how much? Characters occupy how many bytes? A single character? ASCII character? No. A single ASCII character occupies. A single ASCII character occupies how much storage? 1 byte. 2 hex characters. Yeah. Oh, maybe that's what you were thinking. Yeah. 1 byte. Whereas an integer variable occupies how many bytes? 2 bytes. So you'd be dot block 2. So dot block 1 for a character variable, dot block 2 for an integer variable. And they are accessed with direct addressing. So you guys, the most common statement in HOL6 languages, well, unless you're into functional programming, which some of you know, has no assignment statement. Anyway, so one of the most common statements in an HOL6 language, a typical HOL6 language, is the assignment statement. So here's the thing about the assignment statement, the way the assignment statement works. It's you load, compute, and store. That's how the compiler translates an assignment statement. You load, you compute, and you store. And you load from, so when you're loading, you're getting the value of a variable on the right-hand side of the assignment statement. You compute the expression on the right-hand side of the assignment statement. And then when you store it to the variable where? On the what side of the assignment statement? On the left side of the assignment statement. Does everybody see how that works? Okay. So load, and depending, it's either load word or load byte, depending on if it's an integer variable or a character variable. Are you with me? And then scanf is our input, right? So how do you scanf? How would you scanf a character? Instead of doing store byte accumulator from char to char out, which is how we did the output, what do we do? Load byte accumulator from char in, using direct addressing. And then we translate integer input with deci. Okay, now you guys, here we go. Now this is going to be the start of many exercises for us. And what we're going to do is, now I won't call your name out because we are recording this, but we're going to go around the room, okay? We're going to start here and go boom, 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 boom. And if you want to pass, you can pass, and that's fine, all right? And what we're going to do is we're going to together, come let us reason together. Let us reason and try to figure out in figure 5.22, and no fair peeking at the next slide. Let's try to figure out how to translate this program. So what does this program say? Char ch, int j, what kind of variables are those? Globals. And then int main, scanf, you know, into ch and j, and then j plus gets 5, ch plus plus, and then printf, what? The ch, and then the new line, and then the j, and then the new line, and then return 0. Is everybody good? All right, so starting here,
BR main.
branch to main. You had the easy one. Branch to main, excellent. Now, can you think, char ch, so can you think, what's the symbol going to be? What do you, here, the next line is char ch, so that's declaring a global variable. What is the symbol going to be?
CH.
Yeah, yes, so what's going to go here? CH colon. Are you with us? Everybody see that? And now what? Dot block, because we're allocating. Excellent. Dot block, how many bytes? 1. All right, and now there's one more thing. We have to put this trace tag. So we're going to say global variable. And do you know what what did we have for the integer? It was pound 2D, but this is not 2-byte decimal, this is a what? A 1-byte character. So this is going to be pound 1C.
And you have to put the words global variable?
Well, no, not technically, but we always will for documentation. Yeah, question?
That doesn't actually do anything for the code though, right? Because it's after the...
Well, the dot block generates 1 byte of code. That's what the code that's what the code that gets generated is the...
I'm talking about the global variable.
Right, no, you're right. Yeah, that's all for the trace.
Well, the hashtag does, just not the global variable.
Well, this whole line generates 1 byte of zeros. Are you with me? That's what it does.
But you're saying that the computer needs the hashtag thing.
Well, because as I demoed, you want to be able to use the debugger. And so, and I require you to, because we want to, it'll help, because this also helps for self-documentation. All right, next. You're up.
This is J, colon,
J is the symbol, right?
and dot block.
Dot block how much? Dot block 2, and global variable what?
Pound 2D.
Pound 2D, good. Okay, so now next. Good. So now main, colon, and so when we branch to main, we will be branching. Oh, that's very good. Okay, and now what is this scanf, C, blah, blah, blah. So how do we get something into CH? Remember? Load byte, right? Load byte accumulator from where? Yeah, char. The symbol was char in, wasn't it?
Yeah.
Char in. Load byte accumulator. Are you with me? Like here on the previous slide.
Well,
So this is load byte accumulator. Char in direct. Are you with me? And now what's next? Store byte accumulator to where? Now to where? CH, addressing mode. Yeah. Okay, so this is store byte accumulator into what? Into what? CH direct. Is everybody? Yeah.
And these are load byte and store byte instead of load word and store word
Because a character is 1 byte.
Okay.
Yes. Okay, so now how do we scanf the J?
Load by simulator.
Load.
Word.
Load word accumulator. What? Oh no, sorry, not load word. No. Whoa. Sorry, that was way incorrect. Let's go back to this previous slide. Integer input with what? With what? Deci. Okay, so let's go back here. So decimal input into where? J, addressing mode? Direct. And that's it. We do that with just one statement. Deci does that. And what it does is it does all this char in, ch, blah, 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 blah. Remember how we ran it? We ran and we saw how those trap instructions work? So it does it all in one fell swoop like this. Okay? Now, how about j plus gets 5? Have any idea? This is kind of hard first time around. Do you pass? Visitor want to pass, I suppose. And then, what do you think? How do you suppose? Yeah, because this is j plus gets 5 is the same thing as what? J gets, yeah, j gets j plus 5. So what we have to do is we have to get the j, add the 5, and then store it to the j. So what do you suppose this is?
Okay, so load word accumulator.
Load word accumulator. J addressing.
Immediate? Oh no, direct.
Direct. Good. Okay. So next, what do you think? No, hold on.
Oh, sorry.
Next.
That's when you add it?
Add. So what do we add?
Accumulator.
Yes. Add accumulator. And what are we adding?
The 5?
The 5. So how do we add 5?
It's going to be immediate.
Yes.
It's going to be 5.
5 immediate. Excellent. Oh, you guys are good. We're good. 5. Are we getting this? Okay. Now that we loaded the j, we added 5 to it. Now it's j gets.
J gets j plus.
Yeah. So what's the next thing? So what's the next?
So adding is.
It put this got j into the accumulator. This added 5 to that and put it in the accumulator. But now we have to give it to what? Yeah. Store what? Word accumulator to where? J addressing mode?
Direct.
Yes. Very good. Now does everybody, this is good. Does everybody see how this is working? This is what a compiler does. A compiler literally does this. It generates this code. And now what about CH++? Say it again? Well, but it's a character, so load byte. So load byte accumulator from where? CH addressing? Direct. And then next? So that CH++ is like CH gets CH plus 1.
So add
Add accumulator. What?
1.
1 addressing. Immediate, right. Next.
Are we going to store it?
And we're going to, you bet your sweet bippy we are. Store what?
Store byte.
Store byte accumulator to where? CH addressing? Direct. Good. All right. And now printf, now we need to printf the CH. So how do we print the CH? Printf the CH. Load what? Yes. Load byte accumulator what? CH addressing?
Direct.
Direct. Next.
Load by accumulator.
No, we got it into the accumulator. Now it's a character, so we have to send it to the output device.
Oh, would you use stro?
No, well, stro, it's not a string, it's just one character. You can pass if you want. Or you can.
Store byte accumulator.
Store byte accumulator to what? To char out. Addressing? Direct. So that's how you get the character out. Okay. Actually, what happens is behind the scenes, stro does this in a loop. It does precisely this in a loop. We demoed how the trap instructions work. You know how it goes and it looped, you know. Okay, are we good? And then what? Oh, did we have to, oh, you know, we messed up. We were supposed to print out a new line in between. Shoot.
Wait till we do it now.
We just,
Oh, no, sorry, we just did the CH. Now we do a new line. Oh, yeah, so now how do we do the new line?
Would you do like a,
How do you get a new line, how do you get a new line character out? Put a new line in the accumulator, so
word?
load byte accumulator, and what can we put right here? What?
Just the slash n.
Dash n, addressing mode,
Immediate.
immediate, next, next.
Oh, Deso?
No, it's a single character. And it's in, we just did load byte accumulator.
Oh, store to the care out.
Yes, store what?
A.
Byte or word? Store byte accumulator into what?
Care out.
Care out direct. Okay, good. And now how do we do the output the J? Now we can use deso in one fell swoop.
Oh, so you're saying no.
So this is deso from where?
From J,
Addressing
direct.
direct. And then stop dot end. All right, let's see if we did it. Did we do it?
It did.
Did we look at?
We forgot about the other.
Oh, what did we forget?
So this is a new line, but like,
Oh, we forgot the last new line. Yeah. Okay. Well, come on. Okay, look. The compiler, you say to output that new line, the compiler will translate that output of the new line. The compiler will do it. We want to know what
I
the...
understand that, but like the output will look the same.
I know, but that's not the point. The point is, what does the compiler do? Okay? So there it is. So here, let's demo this, figure 522. What time is it?
2:40.
Oh, okay, we'll demo this and then we'll quit. We'll end with the demo, because this is a nice demo also, look. Okay, so here's our demo. Let's go to figure 522. So we'll bring up the help system. Here's 522. Here's our little program. We just learned how to translate. We'll copy it to source. Now watch this, you guys. We will build it. Actually, we should clear memory, then we'll build it. Okay, so here's our object code. Here's our listing. And check this out, you guys. Watch this. Boom. And look what we have down here. A what and a what? A J and a CH. And where is CH stored? At what address? 0003. And where is the J stored? 0004. Is that slick?
Why does it put a 0 in?
Yeah, it's just left over. Just an artifact of the thing. Okay, so here, let's single step through. Boom. So here is load byte accumulator. So there's the M, then deci, the 419, and then add a store word 424, blah, blah, blah. There's the N, 424, boom, 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 and it all works. Are we good? All right, good deal. See you tomorrow.